I know people are in various spots right here. Let's take a look at this as a group. I think everybody got as far as this said 12 Descartes of momentum before and -6 Descartes of momentum before. So the total momentum before was 6 Descartes, just add the two. And therefore that's the final, because momentum is conserved. So afterwards, momentum here, -3 units, plus something, should equal 6. Because the total is 6, therefore if that's -3 plus what gets you 6?
Positive 9.
So this is 9. So the momentum of the 1 kilogram mass final is 9 units. And that's equal to mass times velocity, because that's momentum. So that would be 1 kilogram times the final velocity. So math-wise, this is the problem, 9 is equal to 1g. So the final velocity is 9 meters per second. It's positive, which means that this is actually going to the right. And so that answers the first question. The second question is what type of collision? Well, let's look at the kinetic energy. I know my initial kinetic energy is the kinetic energy of the 3 kilogram mass, plus the kinetic energy of the 1 kilogram mass initially. So it's 1/2 times 3 times 4 squared, plus 1/2 times 1 times 6 squared. So this is 24 plus 18, or 42 joules. And the final kinetic energy is the total, is the final for the 3 plus the final for the 1. 1/2 times 3 times 1 squared, right here, plus 1/2 times 1 times 9 squared. So that's 1.5 plus 40.5, which is 42. So what type of collision is it?
Perfectly elastic.
Yes.
Why is it perfectly elastic?
Why? Because the total kinetic energy before and after is the same number. In physics 151 and 251, I would give them the initial situation, I just say, perfectly elastic collision, and then they would find the velocity of both of them afterwards. But mathematically beyond the scope of this class. And really at this point, there's not much more to, there's one other thing I want to do, but not a lot more to say about momentum, just application at this point. So I'm thinking a week from today, why don't I do something darker? There it is. The quiz on 6 and 7 next Wednesday. It is 2 chapters. The alternative, because the 12th is fall break. The alternative is put it 2 weeks from today, and so you'd be having it right after you come back from fall break. And that, I feel like a lot of my students' fall break means they get to work 8 hours a day or 10 hours a day. So that's why I'm pushing for next week. If the class would like to wait 2 weeks and have it just after you get back from fall break, I'll put that one to a vote, but my preference is before fall break. So, does anyone want to put it off 2 weeks, so the day you come back from spring break or fall break? All right. Sounds like overwhelming enthusiasm for next Wednesday. So, we've got 6 minutes. Yeah, we'll start the next topic. I was debating whether to just send you off loose into the world or to start chapter 8. We are now about to double the number of equations that we have done. So far, we've really dealt with linear motion or translational motion. Those words can be used interchangeably. Displacement, velocity, acceleration. These are all implied to be linear. There is a rotational analog to each of these, rotational, or angular. Whereas again, that can be used interchangeably. Just tradition is, you tend to talk about angular velocity instead of rotational velocity. But if you're talking to physicists and said rotational velocity, he or she will know what you're talking about. So these terms can really be used interchangeably, just as these terms can be used interchangeably. So we have position. And I'll just use S. It can be X, Y, Z, whatever letter you like, or within reason. The rotational analog of that is angle. And you'll notice that the rotational terms tend to have a symbol that is a Greek letter. So the Greek letter here is theta, lowercase. It looks a lot like the uppercase, except for smaller. Displacement, which is just the change in position. Angular displacement, which is just the change in the angle. Although textbook, they generally don't call it angular displacement. That's through what angle did the wheel turn? There's velocity. And the symbol V with the vector symbol. The rotational. Angular velocity. And sticking with that Greek theme, it is the lowercase omega. It is not a W, it is an omega. Lowercase. The uppercase omega looks kind of like a horseshoe with all the left pointing out. Acceleration. You want to take a wild shot at what the analog over here is? Absolutely. And the symbol used for it is, what they'll do oftentimes is they'll go acceleration starts with the letter A. The Greek thing that starts with an A is an alpha, so let's use alpha. So that's what they're doing here. Alpha. Or a fish, it's an alpha. Force has a rotational analog, such as when you close a door, you're applying something, an influence, in order to get it to rotate. This is known as torque. The symbol is a tau. And in my second most obscure reference, in my class, you can also refer to torque as G2 Kabuka. You don't necessarily want to, but I'm just saying, just giving props to them. Let's see, there's momentum. And back to, anyone want to take a shot at what the analog is?
Angular momentum.
Yep. And for some reason, they decided not to go the Greek letter route. And matter of fact, well, probably just makes just as much sense of why you're using P for momentum. Angular momentum is a capital L with a vector symbol over it. Mass. So our first non-vector. There is a rotational equivalent of mass. If you think about mass as being a measure of inertia, Then over here, it has two names to it, and I will flip back and forth what I call it. It's called rotational inertia, or moment of inertia. If you ever see moment of, in terms of if you're talking science or engineering, if you see moment of, it has something to do with rotation. And the symbol for it is a capital I. So, let's live up to that advertisement. We'll just do one because we are almost out of time. We're out of time. Take Newton's second law. To come up with a rotational analog of that, well, you just do the rotational analog of the pieces. So the rotational analog of force is torque. Rotational analog of mass is moment of inertia. And rotational analog of acceleration is angular acceleration. And we have a brand new equation that is true. Momentum is mass times velocity. What is angular momentum?
W omega.
Yes, I omega. And we will definitely get into more detail about what torque is and what moment of inertia is. This is just sort of the opening volley. And I hope, I guess I'll see you Friday. I think I've already posted the momentum lab.
You give us in PowerPoint all the tests,
Oh, have I graded the tests?
all the tests for the chapter, but there is no tests for 7, 6, 7, and 8.